Same boat. I'm a student too.
Class is on August 1st or do we have classes till 15th? Because like exam is on 15th.
15th is the final, so there's no class on 15th. Whichever classes before
I
that
think
is the
15th is
last
the
class.
so I think 13th.
Yeah,
13th is the last class.
yeah.
So we have like oh, 5.5 weeks.
Mhm.
But like initially you said like this schedule on I think Hubble.
So, are you talking about like what topics I
No,
mentioned
like
or how
like
many
with the
lectures?
class schedules.
Yeah.
29 to 2nd, like July 29 to 2nd, that week is the last classes. Is what
Oh, I'll have to check. I'll check. Uh,
and like I remember you mentioning about the final exam being on 15th, so that's why I just wanted to.
okay,
Like
okay,
is it
I'll
like
check. I'll check.
classes ends on August 1st and exams on 15th?
I didn't get a chance to look at the submissions for the homework yet, but how did you feel about it? Generally, are you happy with the final result that you got?
Was not the equivalent of what we but teaching was smooth.
Okay. How about you? Okay. Okay, I don't remember what you showed me, but yeah, if you divided it, I'm guessing it must have been an improvement over whatever you had without dividing it. How about you? Mhm.
This was my
Hmm.
stitching is
Okay,
smooth,
yeah, yeah.
but I was not able to.
Even when I was making the solution, that is what I got first before I did the.
The way you told, right? Instead of going from left to right,
Yeah,
try starting from changing the order, go from like middle to left and middle to right.
yeah.
I tried that as well. When I did that, I think the like, maybe either the homography matrix or the sequence might have been some issue with that.
Hmm.
So I was getting overlapped or like accumulation of images of one over the other. So I was not getting the proper. At least this was like kind of better looking than the other one. So I
Yeah,
went
yeah,
with this
that's
approach.
acceptable. You were saying, Mohit? Hmm. Oh, okay. Yeah, I'll post my solution, and I'll also I know that we didn't go into a lot of detail on how this should be done and what choices can be made. Um,
Was to explore how we the different ways we could do it.
hmm.
And I couldn't because I think because of the time I was not able to try that projecting over the terrain.
Yeah, cylinder. I mean, I don't expect you to do that. It's a bit more involved than just assuming a plane. Um, there's slides. So I normally follow either Dr. Edmund's slides, who's the guy who made YOLO, and he teaches at the University of Washington. Either his or there's a Dr. Snavely, I think that's how you say his name, Snavely or Snavely, Noah. He teaches at Cornell. So for all of the earlier stuff that didn't have to do with ML and deep learning, I was following Dr. Snavely's material, and he has covered the panorama stuff pretty well. I'll just share a link to that along with the solution, and that goes into all the like design choices that you can make and projecting to a cylinder, all of that. So that's, since it's not something that I'm covering in class, I'm not going to ask very detailed math-based questions if I put something from that on the final, but um, just whatever you would be expected to know based on having worked on it, uh, just that would be fair game for the final. Just putting it out there. Not that I've decided what's going to be on the final yet, because um, even what topics to cover after this, I'm sort of figuring out based on response and what I see in the homeworks and quizzes and whatnot. And I know I've been a bit behind with grading so far, but I found out that I was allocated 33 hours for which I can hire a grader. So I've put in a request for that. And once that gets approved, hopefully things should be a bit smoother, because that'll free me up to spend more time on the actual material and coming up with quizzes and all of that. Okay, got about 5 more minutes and then I'll start. I've posted all the recordings on UB Learns. Just yeah, you guys know, right? I didn't like make a post on Piazza and thing because I figured you'd find out anyway. Good morning. On the final, uh, the homeworks, yes, yeah. I thought you were asking about the quizzes for a second. So quizzes are easier than I would say the final would be, since there's no like you're not calculating anything, right? Quizzes, what I try to do is just intuition based and um, a little bit of remembering whatever the highlights of things are. That's about it. Good morning. Yeah.
I found that code on the GitHub is like written by someone else for that
For the project?
yeah, for the project.
Okay.
Yeah, so I'm planning to use it, but somehow someone else trying to run it under the under Windows
Mm.
Windows systems.
Mhm.
It seems missing a lot of like the package. So
Okay.
yeah,
I can look at that with you tomorrow during my office hours if you'd like.
yeah. So what time do you office hours?
I believe it's 10:30 to 11:30, and I'll be available over Zoom. Uh, Link should be, I think it's on Piazza and the syllabus both.
Do you think if I use the Linux or easier?
I find it easier. I mean, if you're familiar with doing things in the terminal, then I'd say it's a lot more robust in terms of like configuring paths for things, because everything would look at like a bash RC or a ZSHRC
Yeah.
for
Because
paths and
I took the robotic algorithm class
Mhm.
like last semester, and they set up the entire system for us.
Oh, is it
But
like a Docker container or a virtual box or something like
yeah,
that?
the virtual box. So
Okay.
yeah, I just don't know if they have that package thing like installed already, because they have like a setup things at the beginning. So once I just run that run the SH files and they just like install everything for me.
Do you already have like a fully booted Linux system? Are you dual booting or
Yeah.
okay.
they-
Yeah, in that
they-
case, I mean, we can set it up on that and I'll walk you through doing it on there. And I guess I can like share that recording also. So if anyone else needs it, we can do that as well. Yeah, if you're comfortable, I would definitely recommend working on Linux.
I'll see if I can make that office out tomorrow. If not, and then I will make a review, see what is.
Okay, yeah. Yeah, if not, then maybe Thursday after class.
Very after class or Friday.
I have
Available.
I have meetings with my advisor on Friday, so I need to prepare for that.
Yeah, I mean,
Tuesday through Thursday, generally, I'm able to set aside some time, but
I'll let you know.
office hours would be easiest for me.
Okay.
34, all right. Okay. How's everyone feeling with the material so far? Are we all able to visualize to some extent what goes on within a network? Feature extraction and then some sort of a model after that that uses those features. Those are concepts that we need to be comfortable with imagining. So I've called these CNN tasks, but they don't necessarily need to be solved with CNNs. Especially nowadays, if you look at the kind of models that we have, most of them use vision transformers and bunch of other fancy stuff like that. But we're not going to be talking about that just yet because we're still learning how to walk. Quick recap, a couple of things that we've already covered. And you might want to keep your eyes and ears open because we do have a quiz today. And some of this is going to be on it. Just putting that out there. CleanIt was arguably one of the first convolutional neural networks that was aimed to solve an image problem and resembles what we consider a modern CNN because it has most of the components that you would expect when someone tells you, oh, hey, I'm using a CNN. You would expect to see convolutional layers. You would expect to see some kind of pooling, which here they're doing subsampling. And at the end, regular dense fully connected layer, which uses whatever features are extracted in the steps leading up to it to make some sort of a prediction. And they were also, this was the first use of the logistic function for activation. And combining that with backpropagation, that this whole pattern of building networks is a very well-known one, and this is where it started from. That was followed by a really large data set. So at this point, we had an architecture that was able to solve some very complex and interesting problems and do extract meaningful information from images. So a really large data set helped push the limits of what can be done with that and sort of explore what the ceiling for architecture is. And this sort of feedback loop has been going on, and it still is an active process where we have a method that you squeeze out as much as you can with the data that you have, and you still have more information that can be teased out from the data set. So you improve your architectures, and that goes on and on. AlexNet was the first good network. that was able to do something really cool and beat the previous state of the art on the ImageNet dataset. It was also one of the first to use the rectified linear unit activation, and the major contribution to the body of knowledge was the implementation on the GPU, which let them speed up computation by about 100 times. We also have been exposed to the idea of thinking of models in terms of sort of loosely stages of feature complexity, where earlier layers that are closest to the input goes in over there. You have a bunch of convolutions and some sort of downsampling operation combined with it typically, and that would extract low-level features like lines and edges. As you go deeper in the network, these start getting more complex, where you have combinations of lines and edges to form curves and shapes. And finally, there's some sort of semantic composition of these mid-level features that are then used to make some sort of a prediction using that. VGG was one of the first models that took depth as an approach, where before that, what we saw with the universal approximation theorem was that in theory, you could model anything with a single wide hidden layer, but turns out depth is also useful to extract information. After that, architecture started getting more complex, where instead of thinking of sort of operational units within the architecture as individual layers, we moved up to thinking of modules, which is combinations of layers as the building blocks of the network. They also introduced the idea of combining multiple sizes of convolutions to extract features at different scales and across channels. And they also modified the network in a way that lets us get outputs at different stages of the architecture, which allows, just makes the process of optimizing and learning a good set of weights easier, because you have information from multiple stages of the model. And the issue at the time was that the deeper you get, when you're propagating your error backwards, there comes a point when you just lose all gradient information, and it doesn't make its way to the initial layers. And those initial layers are important because they're the ones detecting lines and edges and simple features like that. And without those, your composites are not going to be good at extracting anything meaningful. So that problem, we call it gradient explosion or gradient vanishing. Explosion, as the name implies, is when you have gradients being propagated backwards, and eventually they get so large that they become Nan values. Vanishing gradients is what I just talked about, where when you have a saturating activation function, you end up at some stage in between, halfway through the layer, there's a zero somewhere, and then that gradient becomes a zero, and so there's nothing that makes its way back to the start of the model. So one of the ways to deal with gradients getting too large or small is we talked about doing gradient descent in batches. So that was to sort of average out the gradient update that we get over a few samples rather than considering each sample on its own, which reduced computation and let us speed up the process a little bit. So we can apply that logic to what we do with our gradients also. And we normalize our activations of filters spatially and or over the mini batch. So whatever gradient updates you would see for one sample, sort of if there's one sample that introduces a lot of internal covariate shift, it's one sample that is sort of skewing your model's understanding by a lot in one direction that sort of gets suppressed a little bit by all the other good samples. And it would effectively sort of poison your understanding less. Activations, the distribution changes because the weights change. And this makes learning more stable when you're reducing covariate shift, because the outputs that you would see from one batch of samples would be similar to the outputs you would see from another batch. A 32 by 32 by 16. So there's 16 feature maps over here. This is the output of some convolutional layer that had 16 filters. And with a batch size of 64, when you normalize the activations across all the images, you get a batch of 64, and then that gets applied for each filter. So there's 16. And the way we normalize is by calculating the mean and variance of gradients that you would find within the batch and normalizing them to 0 mean and 1 variance. And we do that by subtracting the mean, dividing by the standard deviation, and that lets us stabilize our training process. And this really helps with training models that are significantly deep. Mean 0, variance 1 means that it's in the good domain of most activation functions. Each image is presented to the model along with other images. So there's a sort of frame of reference. There's some context for what where that sample fits in the entire distribution, because they're not looking at just one facet of it in isolation, but you get a sort of sense of what to expect. And it stabilizes training, which lets us use a larger learning rate, because your weight update is informed by more samples within each batch, which consequently lets you make bigger update steps. The GoogleNet architecture, this isn't officially what it was called, GoogleNet V2 or InceptionNet, but the architecture we saw earlier with the inception blocks in it, they added batch norm to it, and that improved things. This is basically the architecture, what layers and what sizes at what position, and what the operations are in terms of pooling and projections. Another idea that was introduced to deal with the propagation of gradients through networks was what they called residual connections or skip connections, where typically what we do with a layer and a set of weights and an input, whether it's a feature map or the original image that we're using, that goes into a layer, and typically it's just the output of that layer, the forward propagation. But what we do with residual connections is you take the original input to that layer and just sort of reroute it so that it's also present at the output part of that layer. And what that does is when you pass an image through a convolutional layer, you get a bunch of features, and those progressively get more and more complex. And that's kind of a lossy process because you're losing whatever information went into the layer to give you those features. Using these, you're able to pass along some of that context to the output, and your next layer's input will include not only the feature map that is computed at the previous layer, but also the input to the previous layer. So there's context for what input led to finding these features. And it helps with telling the model what transformation is being learned, and helps with learning how to modify the set of weights according to what input is present along with it. And the other cool thing is this, what I spoke about just now was when we're going forward. And if that connection is over there, when we're going forward, then what happens when we're going backwards? Any guesses? So for context, this is what an entire architecture would look like. And we're going forward, whatever the output of this first convolution is, that goes into another convolution, but along with that, it also gets passed forward. So there's these connections. Would that do anything when we're back propagating our errors? It's a binary question. It could either do something or not do something. What do you guys think? Hands if you think it helps. Not a lot of faith. Well, this is up here because we're talking about it in the context of exploding and vanishing gradients. So you have a bunch of, think of them as like wires that you're using to sort of short the network in places. They're still there when you're going backwards. So if you have whatever gradient information you have at the end also gets passed along to previous layers in addition to whatever would go through. So the benefit should be pretty apparent by now. Since we're talking about this in the context of vanishing and exploding gradients, or which happen because you don't have a good way to pass gradients all the way to the start, well, you have a bunch of extra connections over there, so gradients flow better. There's the one-by-one convolution blocks also that are being used. So this is something I had briefly touched upon earlier. When you have a bunch of feature maps that you get, so you use 64 filters for a convolutional layer, you end up with however many channels you had in the input. It was, I don't know what 64 times 3 is, so I'll say 32 instead. 32 filters, 3-channel image goes through a convolutional layer, you end up with 96 feature maps at the output. So that math I can do. To find some relationship between all of the feature maps that you get, or even when you have multiple channels, if it's your very first input, and you want to extract information between channels, a one-by-one convolution is just one pixel with however many filters you ask for. So it's basically convolving in the channel dimension and allowing you to extract information across channels. residual connections, that sort of channel information mixing, all of that put together, batch normalization, all the things we saw together allows to build very deep networks, over 100 layers. ResNet 121 is one of the common ones that's still used as a feature extractor. This is the 34, but yeah, there's a couple of standard pre-trained ones that are still used quite often. So we dealt with okay, let me put it this way. For each image, convolutions, we're talking about 32, 64, however many filters. That's a lot of filters that we're applying. And if it's 3-channel, 4-channel, whatever input, then your number of feature maps increase by that factor. And it's a lot of computation. So we dealt with our gradients. So maybe we can try to make it a bit more efficient, compute things less often. One idea to tackle that was grouping our convolution. So instead of applying every filter to every input image, this is helpful when you're a bit deeper in the network. So at your input layer, you probably don't want to group them because you only have like 3 channels. But once you get up into like the 32, 64 channel count range, it starts to add up. So we group them channel wise and have filters that correspond to each group and only apply each filter to its corresponding group. So for a 32 by 32 by 256 channel input going into a 3 by 3 convolutional layer, and there's 128 filters. If you had to do that directly, then that's 256 times 128, however much that is. I'm not even going to bother doing that. But instead, what you can do is break it down into 32 groups. So your input, the 256 channels, you bucket them into groups of 32, which gives you 8 groups. And then you run 4 filters, which is 3 by 3 by 8. So your filters also have 8 channels over here, and run that on each group, and that gives you outputs for each group. And we can merge those results at the end, either by concatenating them channel-wise, which retains all of the information, or the other option is kind of like how you would grayscale an image. You combine the information from all the channels and flatten it into however many groups you have. So that is sort of, it's better for memory, but you're losing information. So that's an informed choice that you would have to make depending on how the model is functioning for whatever data you have. ResNext, with an X in the name, is a version of ResNet that incorporates this idea of grouping convolutions into the architecture. And where you'll be able to see that is if you look at the total number of floating point operations, which is an approximation for how much computation one pass of the model takes, or how much computation is involved, and also the number of trainable parameters or weights and biases. They're comparable, almost the same, but the number of filters that we have is a lot more. So we have 128 filters each instead of 64s over there. And this is grouped into blocks of 32 channels. And we're able to extend that same addition of filters throughout the network. So effectively, we're extracting a lot more features for the same amount of computation. The other way that you could have gone around incorporating the group convolution approach would be to keep the number of filters the same, and you would end up with a model that's much smaller and faster. So those are the two paths that they could have taken, and this is what they chose because people were already comfortable with the idea of using ResNet and how many parameters it has and how fast it runs. So it just made more sense to shoot for more representational power over speed and memory use. This is, I mean, all of this so far is from Dr. Redmond's slides, and I think these are at least a couple of years old. So if you look at what's going on with ImageNet today, this is probably a bit higher. The first big jump was when we switched paradigms from SIFT and manual feature extraction, sort of human expertise reliant approaches. We switched from that to a CNN based. That was a significant jump of almost what is this, top 5-10% classification accuracy. From there, the next big jump was going to BGG when we started going deeper and stacking a whole bunch of convolutions together. And it's sort of leveled out after that. And the returns are diminishing, but they're there nonetheless. You guys can pull these up to see what the state of classification on ImageNet is. There's now the sort of focus has shifted a little bit more towards what paradigm of training models is being used. So weakly supervised and semi-supervised approaches have become more popular, and a lot of the models we use today are trained in that setting. So benefits of that, if you would recall what semi-supervised was, you only have labels for a subset of the data, which in turn means that you have to spend less time on annotating your data, figuring out what classes are. So you train it on a subset and the model generalizes to the rest. There's also contrastive training, which is where you only tell the model what a positive class is in relation to a negative class and an anchor class, and you supply all of those together with the objective of learning how to partition the sample space based on that relative relationship. So at this point, we know how a neural network works. We know what CNNs do. We know how to classify and also regress values, either spit out values from a continuous distribution, or we do something with them, which is apply something like a softmax to convert them to class probabilities. There's all these other tasks that I think now it's safe to say most of us have at least heard of. And the underlying principle is still fairly similar because that's how we approached it when we were not dealing with neural networks. The typical approach is you extract features and then use them to make some sort of a decision based on it. So how do we adapt CNNs to that? The first point up here, other data sets. All of these architectures were sort of pitched and first demonstrated on images of scenes from the natural world, the kind of images that you would see if you opened your photo gallery on your phone. To generalize to problem domains outside of that, there's a bit of a data scarcity issue. When you think about things like, say, someone had pitched an idea for a project involving thermal imaging and drones, and data for that, I would imagine, is kind of hard to come by. So to develop a solution for that, we'd have to be able to retain some of the understanding of dealing with the regular kind of scenes and images and be able to tweak that a little bit to apply them to a different looking image. Since shapes and structures, if it's still the real world in 3D, but sort of a different spectrum that you're looking at, which is what thermal would do. Or if you're looking at, say, infrared or ultraviolet, those structures, it wouldn't be far-fetched to say that you might still find something resembling the same structures in those images also. So some of this knowledge should be transferable. And most data sets, especially if you're trying to solve a problem yourself and collect data to do something, you're not going to be able to generate 1.2 million good images with thousands of classes. So we need some way to get around it with what we already have. This brings us to the idea of transfer learning. So we start with any good architecture that works on a data set that's similar to the problem that we want to solve. So considering ImageNet and this looks like VGG, we train it on a good existing data set, which gives us a good set of weights. And we already know that we can think of this in terms of feature extraction followed by a decoder that's then used to make a prediction. So train it on ImageNet, freeze all the parts that are used for feature extraction and representation learning, and get rid of the part that makes the prediction, that learns the, because the last layer is the only one that has a mapping between feature space and the kind of predictions you want. It takes features and transforms them into predictions. So we want to use the same mechanism to extract features because we know it's good, and make different make a different function to adapt to the different looking feature maps. So where you would see a tree in green, when you're looking at it in the thermal spectrum, if it's a hot day and the soil is hot, you'd see red soil and like a blue tree or something. So to adapt to that domain shift, you would get rid of just the last part and only train a classifier at the end. Replace it with another layer to interface with this once it's flattened, because it's 512 times 4 times 4, so that's yeah, that works out to 4096, and then you have a final however many classes, so 1,000 classes, and those many values that it spits out for probabilities. The key takeaway is that for the other stuff, segmentation, object detection, captioning, regardless of what problem you're trying to solve, it's just a matter of choosing the right loss function. So as long as you're able to formulate whatever problem you're trying to solve as an optimization problem, where you have a way to measure how good or bad your guesses are, you can repurpose the same pipeline to do different things. The first problem that we'll be talking about is semantic segmentation, and breaking it down. So the reason there's a semantic does anyone want to hazard a guess on? Okay, let's start with what's segmentation? What would the segmentation do? We saw what it does with k-means when we clustered the image of a flower and leaves into two colors. If just casually speaking, if you wanted to explain that to say a graphic designer or someone who's doing Photoshop, and you want them to do what how would you describe what this is? Separate problem, but related, yes. If you think of it in terms of depth, sorry, that is how it is solved. Sure. Just what I'm trying to say loosely is like you're separating background and foreground, right? You say depth estimation. You could use that to segment things, but basically you care about object detection. In contrast to segmentation, has more to do with location than class of object. So essentially, we want to separate things that would occlude each other when you look at them in a straight line, because they're in the same path, but they're not at the same depth. And the way we do that is by the way we represent that information is in the form of what's called the segmentation mask, where corresponding to the region that there's a person present, you would assign pixels with labels person, which in pixel value terms would be just some discrete value. So you could, and typically these are stored as separate channels. So you would have a person channel, and wherever there's a person, you would have a 1, and everywhere else it would be 0. So if you look at just the channel corresponding to person, you would only see outlines of people and nothing else. And then there's car, tree, whatever. So up until now, we were only dealing with this part, right? Extracting features, building more and more complex representations of a flat image, and condensing that to a sort of vector representation. So you can think of this as compressing it. You're it's kind of like a hash of something, but it also has meaning. And in theory, you would be able to, since you're able to make a prediction using that for what class it is, then that indicates what combination of high-level features it has, and it retains information from the original flat distribution of light representation. Um, so if you flip one of these around in a way that lets you generate uh, information from this condensed representation, you could ask it to, you could supply this as the target where instead of having individual values like class labels or the output of the sign function, you have an entire image as your output. Um, and the image contains the segmentation mask with class labels. This sort of architecture pattern is pretty popular. Even when a paper or architecture doesn't explicitly talk about it, um, the sort of style of extracting features progressively and condensing them into a vector, and then using that to do something that upscales it again. You'll see this called as an autoencoder style architecture or an encoder-decoder network. Um, the one thing we didn't talk about is how to do the upsampling part. So we're familiar with convolutions. When we're going forward, uh, applying a convolution is a sort of lossy operation that performs a weighted sum on whatever input that layer receives. Deconvolution is the opposite of that, where given a smaller region, we have to guess what the larger region would look like, given that this is your prior. So when we were dealing with just our VGG or ResNet or encoder only followed by a fully connected layer at the end, when we're doing back propagation, whatever errors we find are still making their way to each weight. So whatever error you have at the end would have to propagate backwards through it in a way that affects all the weights at every layer. So essentially, we are doing deconvolution in the backward phase. The only thing that's changed over here is that we're now also doing it during the forward pass. So it just flipped one of these, put it over here, forward, backward, and we're doing convolution, deconvolution both ways. This encodes information into, you would see this called the bottleneck layer or an embedding layer or a global latent space. from which eventually you're able to get back whatever it is you want. And to solve segmentation, you put segmentation masks in there. Course features, well, these are a very condensed representation of the input from which we're getting fine-grained predictions. There's still the issue of vanishing gradients and exploding gradients, just information not propagating very well. So this was a step in the direction of being able to do segmentation, but we can make it better. This is still the same architecture, but instead of going like that, we just changed the way we're representing it. And this is convenient because we're now doing something similar to the ResNet, where we put skip connections and also pass intermediate representations to their equivalents on the other half. And this architecture is still used very widely. It's called UNet. Segnet was another paper that also did something very similar. That name isn't really used much anymore, but UNet style networks are still very popular and used a lot, especially in medical imaging. It's all I ever see when I'm doing literature review to solve some new project that lands on my table. Progressive downsampling followed by upsampling to segment your image and predict a segmentation mask. That allowed us to preserve a lot of context similar to ResNet. Now, preserving context is useful in terms of improving the quality of predictions. To make things a bit more efficient and also deal with the challenge of scale, we covered Gaussian pyramids earlier, where you calculate multiple versions of the same image at multiple scales. And what that allowed us to do back then was apply one convolutional filter to different scales and find features at different scales. So applying the same principle here, pyramid pooling is an approach where you take your outputs from a convolutional layer and apply convolutions of different sizes. So you start by pooling at different sizes to get different sized feature maps, and then you have a convolutional layer corresponding to that feature map size and apply that, which allows you to find features at multiple scales in one step. And then to retain all of that information in a way that you can extract meaning from it across scales, you would concatenate all of them channel-wise and then use something like a one-by-one convolution to get information, either by adding them or just holding on to the outputs of that one-by-one. And once you have that, upsampling it ensures that they're all of the same size so that you can stack them channel-wise, and then that gives you better predictions because you're able to find people both up close to the image and also someone really far off in the background, because you're looking for the same set of features at different scales. How that looks is when you plug it into a UNet is you're downsampling path, which is the encoder, relatively unchanged. At the last stage, you're generating all of the intermediate outputs that would have been passed over here, and you can upsample all of them in one go. So since you have features from all scales, that reduces a bunch of computation that you otherwise would have had to upsample individually for each scale. But we already know what features are present in each scale since we have everything together, and just upsample in one step and reduced a whole bunch of computation directly giving us the prediction. Google took this idea and said, well, instead of applying our convolutions to feature maps of different scales, how about we just change the window or the receptive field of the convolutional kernel. So each element, when its response is being computed for a filter, normally you would have it overlap exactly, but instead of that, the address convolutions look at a wider receptive field in the input that it gets and allows extraction of features from scales that are larger than the filter. And it's essentially just spacing out the pixels that it would map to. And that then gives multi-scale information. So this part, since it's a reusable feature extraction block, this can be pre-trained on ImageNet as the initial part of a VGG or ResNet that's learning to classify those 1,000 images. Then we freeze that, chop it off, and then the final fully connected predictor gets replaced with this part, which then changes what we're predicting to class labels at each pixel position instead of classes. Fine tuning is freezing this part and only updating parameters, that is the weights and biases of this branch of the network. And we talked about how influential ImageNet was for classification, and Pascal VOC is a data set that did the same thing for segmentation and really pushed the envelope on what was possible. 20 classes, close to 10,000 images, and each pixel has a label corresponding to what class of object is behind it. We ended up with some pretty good results. We're able to tell apart where people start and end, where vehicles start and end, where signs are. But there's still a bit of a problem with this. Can anyone guess what's not great about these predictions? You know that, okay, well, what's wrong with this region over here? Or say that, like, does that look like a person's outline, that whole blob? What would it look like ideally? Who said that? Louder? Yeah, yeah. That's precisely what we would like to be able to do. So it's good that we know that there's people or a person over there, sure. Ideally, we should be able to tell apart which pixel comes from which person, right? If I have, say, two people holding hands, then I would like to know which pixel comes from which person's hand. So semantic segmentation that we were doing had to do with classes um, broadly. Uh, one step finer than that would be to define the problem as instance segmentation, where what you care about is not just the class, but also which instance of that class um, is being segmented. So we're missing a few pieces to solve that problem at the moment. And one of those pieces, uh, these are a few examples of images in their segmentation mask from Pascal VOC. This particular image has that issue quite prominently, where we're not able to tell where people start and end. They're just one amorphous blob, more or less. Same thing going on over here. So we need to know locations. And for that, we will need to learn about and understand how object detection works, which we will be doing in the next class. So today, we have a quiz. So I would like everyone to open up their computers, fire up Lockdown, and I'll make the quiz visible in just a second. People who have issues with Lockdown, let me know. I have printed copies of the quiz here. I have 6, I believe. So just, I don't know, wave at me or put your hand up or whatever if you're having trouble, and I will get you a printed copy of the quiz. Okay, quiz should be visible on UB Learns, and all right. How do I- Yeah, okay. Anyone need a printed copy? I want to remind you guys that if you feel like you're having a hard time with the quiz, then everyone else probably also is having a hard time with the quiz. So just answer what you know, and that also someone, I saw a hand here. Yeah. Anyone else? Okay. What was I saying? Yeah. Sticking to what you know helps not only you, it helps the whole class in 2 ways. Yeah. Print.
Password is not.
Oh, okay. I'll check that. Might be an uppercase H, probably. Pretty sure that's the password I put. Okay. Oh, okay. That worked? All right, awesome. And I'll just check the other password also in the meantime. Yeah, that's also uppercase F. Okay, that should do it. Yeah, as I was saying, just stick to what you know. There's, I mean, apart from the obvious benefit of no one getting in trouble, there's also it also helps me sort of gauge if I need to be, I don't know, visualizing things more or spending more time on things, and just the uh, general state of everyone's understanding. And it also doesn't skew metrics for the class. So um, if you guys all, I don't know, if there's people doing things they shouldn't be doing, then you might be what's the word? Cheating your classmates out of getting a curve higher, because if there's a couple of people sitting much higher than everyone else, then that sort of makes it harder for me to curve everyone else up. I only need glasses to read, so my distance vision's really good.
Got like swiped out and
I give you a print.
yeah.
Okay. Yeah. You have questions, Roger?
I'm sure really fast.
Actually, it won't let you exit out of lockdown without a password. That's
Oh, like if I, oh, I guess like I just hit submit and then it just let me.
I don't know. It was an option while I was setting it up, so I just
Okay, I was
put
just
it in.
making sure it was.
No, you're fine. Yeah.
For this question before I submit it.
Sure.
Oh.
I thought I posted quiz one solutions.
Yeah, but I haven't had these two.
Oh, right. Yeah, I'll do that. There's.
Yeah, so that's why I'm wondering. I just take the picture.
Yeah, sure. Let's do an homework too. I'll post the solution tomorrow. Project question. No, yeah, 7 points is usually more than one. Yeah, I'll keep that in mind for the next time I print it. On UV Learns normally it shows up select all. Yeah. Okay.
Like for the previous submission of group thing, I
Mm.
didn't submit, but my teammate did submit for the document is necessary that I have to submit.
No, that's fine. What? Well, okay. Yeah. Your team. Who's your teammate?
Only submit.
Why do you have a phone out, man?
My phone.
Okay.
But in the last quiz I wrote in paper, those marks are not.
Yeah, I didn't grade it yet. I'll, I
When
have it
can we expect?
tomorrow.
Thank you.
How do you feel? I'd put a timer on the paper if I could. I mean, SVMs are from before that. Gradient descent was also introduced before that. K-means was introduced before that. What else? Hmm. Don't worry about it too much. You'll be fine. These, I still have last quiz paper submissions to grade. So I'll probably do these and those tomorrow. For quizzes, everyone has the same amount of preparation, right? So, I mean, no one has any more information about what's going to be on the quiz than anyone else. And the letter grade is going to be curved at the end. So just sorry. No, I mean I don't really get the reasoning behind assigning someone a letter grade based on how everyone else did in the class necessarily. But yeah, I mean, I'll be looking at the distribution of grades basically and figure something out. Yeah, you're welcome.